All right, guys, let me kind of explain this concept a little bit. I think we started talking about it like the very end of last cycle before vacation. So let's review a couple things and then we'll jump to the Shad Pack and we'll do the problems there, okay? So let's take a look here. I just took this out of the book. Essentially what we're trying to do is make some connections about the original function that we start with, the function's first derivative, which is this graph, the green graph, and the function's second derivative. Okay, so we want to use the information that we have from the first derivative's graph and the second derivative's graph to make statements about the original function. Okay, and then of course we're also going to be making statements about these two together. All right, so depending on what information I give you, whether it's about the first derivative, the second derivative, or the original function, I need you to be able to fluidly go through the properties of these graphs, okay? A little confusing at first, and I get that, all right? So this is going to take a little practice. Not a hard thing to do, but it's not super intuitive, all right? So let me kind of go over some of the things that I'm going to ask you, and we'll just review a few things as we go, all right? So the first thing I would ask you is to determine the critical numbers, okay? So what are the critical numbers? Well, that's where the derivative is either 0 or undefined. All right, so let me take a look at the first graph. We have the first derivative graph. I can look at this automatically and see that there are two critical points, or critical numbers, critical values, they're all the same thing, two critical points based on the first derivative of the function. And I know that this must be a critical point right there because the derivative is 0, and I know there's got to be another one right there. Right, 4/3, it's given to us in the problem. So if I asked you for the critical numbers, or the critical points, or the critical values, or if I use the word critical, you're going to look at the first derivative and tell me where it's either 0, or you have a hole, or you have some kind of asymptote, or something like that. It's 0 or undefined, all right, and that's in the first derivative. That would be your first goal, all right, because there's going to be a lot of important things happening between these critical points. Another thing I could ask you is, where is the original function increasing? Well, that's anywhere that the derivative is positive, right? Because if the function's increasing, you're going to have a positive tangent line, all right? So anywhere that the first derivative is above the x-axis, that's where it's increasing, all right? So it looks like there's two intervals where the original is increasing. So from this section of the graph, the original function must be increasing, right? And then also here, because they're positive derivatives, and that is shown as being above the x-axis on the first derivative's graph. All right? Similar idea for where is f, the original function, decreasing. Well, that's anywhere where the first derivative is below the x-axis, so I can pull that interval. All right? So I'm going to ask you to find the critical values, find where it's increasing, find where it's decreasing. And that's what the first derivative can tell you. The first derivative can also tell you about maxes and mins, right? Local extrema. So I could ask you, where does the original function have a local max or min? Or maybe it doesn't have one at all, right? So we're going to use the first derivative to answer this question as well. So if you're dealing with, let's say, a local minimum, right? That's where the derivatives is negative, and then it hits 0, and then it starts positive, right? So the derivative is negative, like in this little section here, and then it hits 0, and then it becomes positive, right? So I know that this must be a minimum, right? Because the derivative changed signs, and it changed specifically from negative to positive while hitting 0, right? It was a continuous motion there. And then similarly, if I want to look for any maximum points, I'm going to look for where the derivative changes from positive to negative. So like in this area here is positive, and then it hits 0, and then it becomes negative, right? So I know that this one has to be a max, okay, right at 0. So that's what the first derivative can tell us, right, about the original function. And then we've started to talk a little bit about the second derivative, and we're trying to understand what this can do for us. So the big thing with the second derivative now is it tells us about concavity, okay? So the first derivative will tell us about increasing or decreasing, and then the second derivative tells us the way that it's increasing or decreasing. It might be concave up, it might be concave down, or vice versa, right? For decreasing or whatever. All right, so another common question I'm going to ask you is, where is the original function concave up? All right, and that's anywhere where the second derivative is above the x-axis, right? So we have a positive second derivative here, so on this interval to infinity, that function should be concave up. Anywhere that it's concave down is where it's below the x-axis, right? So you have a negative second derivative, right? All of this section, and we have a little issue here at 0 that we're gonna have to talk about. All right, so concave up, concave down, very simple. Positive second derivative tells you that it's concave up. A negative second derivative will tell you it's concave down. Pretty basic stuff there. All right. And then I might ask you to list some inflection points. So I might ask you, where is there a point of inflection on the original function f, right? So if you're looking for inflection points, that's where the concavity changes, okay? So if we look, we're looking for a sign change, essentially. We want to know, where does the second derivative go from being, let's say, concave down in this section, right? This is where it's negative, and now it's concave up here. So that means that this has to be a point of inflection because it changes concavity. Just like in the first derivative, when the first derivative changes signs, it tells us about extrema. Okay, and this is pretty much where we are in our functional analysis through calculus, is understanding what the first derivative tells us and what the second derivative tells us about the original function. Okay, so that's the big idea. So we're going to have to take this idea and put things together algebraically. All right, and then I'll show you how some of these problems work. But this is essentially the idea.